All right, on 428, section 7.3, they remind us of logarithms. So we're going to go back through and look at all of the things that we've learned previously about logarithms. They're going to move through it pretty quickly because it's all review material for us. All right. To begin with, when we're working with a logarithm, a lot of times what we like to do is to switch it over to its exponential form because we're typically more comfortable with exponents. So if you take a logarithm and you rewrite it in its exponential form, you take its base of a, and we would raise it to the answer of y and set that equal to what we were taking the log of x. So that would be a to the y equals x. The reason that we can do that is because exponentials and logarithmics are inverses of each other. They undo each other. We'll see a lot more about that today. So like an example of that is if you have the log base 2 of 8 is equal to 3, that's just 2 to the 3 equals 8. So we could write that as 2 to the third is equal to 8. So for example 1, they ask us to evaluate these logarithms, and it's probably easiest if we do that by switching them to their exponential form. All right? So for this first one, if I switch log base 3 of 81 to exponential form, what would that be? Yes, 3 to the x is equal to 81. Now, there's some of these that once you switch them over, you'll automatically know what they are. Like you might know what x is in that case. But there will be others that maybe you wouldn't know once you got to that stage. And so if you are unsure, what you can do is get your bases the same and set your exponents equal to each other. So if I rewrote 81 with a base of 3, that would be 3 to the fourth. So now my bases are the same, so I can set my exponents, x equals 4, equal to each other. And so my solution would be 4. All right, look at the next one. Log base 25 of 5. What is that in exponential form?
Y. 5x. Just like 5x equals 0.5.
All right, 25 to the x is equal to 5. So I need to rewrite this with a common base. What's the common base going to be? 5. So if I rewrite 25 with a base of 5, it would be 5 squared. So then I have a power raised to a power. We talked about laws of exponents. So when you have power raised to a power, you multiply. Yes. So now we have 5 to the 2x is equal to 5 to the 1. Now my bases are the same. I can set my exponents equal to each other. So if 2x is equal to 1, divide both sides by 2, x is equal to 1/2. And once we see it, it makes sense. Otherwise I might be sitting here going, well, 25 to the 1 is 25. How am I going to get back to 5? Oh, yeah, 25 to the 1/2 means square root of that. Okay, I can see where I'd get that. All right, look at the next one. If we take the next one and we switch it to its exponential form, that would be 10 to the x is equal to 1/1000th. I got to get my bases the same. So what could a common base be for 10 and 1/1000th? 10. All right. So if I think of 1/1000th as its fraction form instead of its decimal form, it might be easier. What is 1,000 as a base of 10?
The third.
10 to the third. And how do I move it? Negative 3 would let me move it across that division bar. So now my bases are the same, and I can set my exponents equal to each other. All right, so let's talk about some other things in regards to logarithms that we know. We've mentioned that exponentials and logarithmics are inverses of each other. So if they are, here are some things that will be true. I already know what the exponential function looks like. You cannot take the log of 0 or a negative number. So you can only take the log of a number that's greater than 1. So for that reason, we're going to be looking at the increasing function for our exponentials. If I reflect that in the line y is equal to x, that will create my logarithmic function down here. And again, a way that I can see that is if y is equal to the log base a of x, if I switch that to its exponential form, that's a to the y equals x. Well, this is y equals a to the x. This is x equals a to the y. So again, we can see x and y have just switched places there. So we can see how they are inverses. So some things about that will help us. We could go through then and say whatever was the domain of the exponential will be the range of the logarithmic, And what was the range of the exponential will be the domain of the logarithmic. We also can just look at the graph of that logarithm and easily see what its domain and range are. So if I'm looking for the domain of this guy, I can say that it goes off to infinity this way, but as I come this way, I have a vertical asymptote at 0. So I'm never going to go past 0. I'm going to go right up to 0 but not touch it. So my domain is going to be 0 to infinity. Range, however, is going to be all real numbers because you can see it going off to infinity here and going off to infinity down here. And again, you'll notice that that's just the opposite of what we had for an exponential. We also had two landmarks when we worked with an exponential. Our two landmarks for the exponential was that we had a horizontal asymptote at 0. So for the logarithmic, we're going to have a vertical asymptote at 0. So x equals 0 will be our asymptote. For the exponential, we had a landmark of a y-intercept at 1. So 0, 1 was a point on our exponential. For the inverse, then, if you switch 0 and 1, that would be 1, 0, right? So that's going to give me a landmark of 1, 0 as an intercept for my logarithmic. So the same way we had those two landmarks to help us draw our exponential, we have a similar set that we can use for our logarithmic. All right, couple of properties about logarithms. Since logarithms and exponents are inverses of each other, we learned those cancellation equations in section 7.1 that said if you do a composition of a function and its inverse, they'll cancel each other out and just take you back to x. So that holds true here too. If I take the log of an exponential, as long as the bases are the same, they'll undo each other and take me back to x for all real numbers. If I have an exponential raised to a logarithmic, so that again is a composition of a function and its inverse, as long as their bases are the same, they'll cancel each other out and just leave me with x, as long as x is greater than 0, because again, you cannot take the log of 0 or a negative number. A couple other properties of logarithms. You have the log of two things that are being multiplied. You can break that into two separate logarithms that are being added. If you have the log of two things that are being divided, you can break that into two separate logs that are being subtracted. And if you have the log of something raised to an exponent, you can move that exponent out in front as a constant being multiplied times that logarithm. Some of those properties sound a little familiar. Well, if you think about it, with exponentials, when your bases are the same and you're multiplying, you add. When your bases are the same and you're dividing, you subtract. So definitely some similarities with our inverses there. So look at example 2. For example number 2, it says use the properties of logarithms that we just learned to evaluate the following. And they give us log base 4 of 2 plus log base 4 of 32. So what can I do with that? Multiply. When I have two logs that are being added, I can combine them into one single log that's being multiplied. So 2 times 32 is 64. Now I'm right back to what I was doing up here on the top of the page, right? Let's switch it to its exponential form, which would be
4x equals 64.
Yep, 4 to the x equals 64. And again, that may be something that you know off the top of your head, but if not, we would just want to rewrite 64 with a base of 4. So if I rewrite 64 with a base of 4, that's 4 cubed. So now my bases are the same. I can set my exponents equal to each other. All right, look at the next one. 2 logs being subtracted. How can I simplify that? Divide, right. So 80 divided by 5 is going to give me 16. Switch that to its exponential form, and I'll have 2 to the x equals 16. And again, you may know that off the top of your head, but if not, you could rewrite 16 with a base of 2, and we would have 2 to the 4th. So once my bases are the same, set my exponents equal to each other, so x equals 4. On the bottom of page 429, they also give me some limits, some limit laws for logarithms. And they tell me that if a is greater than 1, because that has to be the case with a logarithm, then the limit as x approaches infinity of your logarithm is going to go to infinity. Okay, come over here and look at the graph. Here's the graph of the logarithm, right? So as x goes to infinity, our y value is absolutely going up, up, up to infinity. So if we know what the graph looks like, we don't have to memorize that limit law. Same story over here. They want to know the limit as x approaches 0 from the right of that log. So as I'm coming in and I'm approaching 0 from the right-hand side, that shoots off to negative infinity. And again, that's exactly what my limit law says. So I do need to know those two but I can get them off of the graph instead of having to memorize them. So then that helps me when I get to the next example and they want me to evaluate the limit as x approaches a negative infinity of the log base 10 of 1 minus x. All right. To start off with, I'm definitely going to want to do some substitution because I don't have any properties for the log of a quantity. So let's replace that quantity and say, okay, let's let u be 1 minus x. So now I've rewritten this as the log base 10 of u. But if I'm going to replace this x with a u, I also have to replace this x with a u. So we can come down here and think about, as x was approaching a negative infinity, what is u going to be approaching? Well, if I come over here and I put a negative infinity in right here, I've got 1 minus a negative infinity. Now again, we're not referring to infinity as an actual number. It's still the concept of something getting larger and larger without bound. But if I have 1 minus a negative infinity, that would be 1 plus infinity, right? So something getting infinitely larger without bound, and then 1 added on to that would be what? Infinity, something getting infinitely larger without bound, right? So I can come over here and put my infinity in. Now that is a perfect match for that limit law that we just had a moment ago. We mentioned yesterday when we were working with exponential functions that we had a natural exponential function, showed up often in nature, called the natural exponential. So it makes sense then that its inverse would be called the natural logarithm. And we have a couple of abbreviations with our logarithms. If you have a log that does not have a base, it is assumed to be a base of 10. And that's called a common logarithm. And that is the log button that you see on your calculator. It is a base 10, the common log. If you have a log base e, because that's the other one that gets used so often, we abbreviated that as well. And we abbreviate log base e as ln. So if you see log base e of x, that's the same thing as ln x. Now, ln or log base e, either one, has all of the same limit laws that we learned with the regular logarithms. They also apply to the natural logarithm. So for instance, if I come over here and I think about what a regular exponential function looks like, since e was just 2.7, remember that we said anytime a is greater than 1, then you're going to have that increasing function with those two landmarks, and we saw that y equals e to the x graphed that same way as a to the x, since e was a number greater than 1. Similarly, down here, then if I reflect that natural exponential function, I'll get the natural logarithmic function. And the same thing is true. When we were looking at all of those laws for logarithms just a moment ago, that was log base a, where a was a number greater than 1. E is a number greater than 1. So we literally can just put e in the place of a. And so you'll notice I still have the exact same domain, the exact same range, the exact same intercept, and the exact same asymptote. None of that has changed. We also could rewrite those cancellation properties that we were using in the regular logarithms to be specifically for a natural logarithm and a natural exponential. So we could say that if you take the natural log of the natural exponential, since they're inverses, they undo each other and cancel each other out and take you back to x for all real numbers of x. If you have a natural exponential and you raise it to a natural logarithm, they'll cancel each other out and take you back to x for all values of x greater than 0. And then there's another property they give us down here, and that is ln e is equal to 1. You could reason that out with common sense, or you can memorize that property as well. All right, so example number 4. For example number 4, it says find x if ln x is equal to 5. So I'm trying to get x by itself. A couple of different ways that I could go with this. First, I could do what we were doing previously, where I was switching the logarithm to its exponential form. So if I'm going to do that, I might prefer to rewrite ln as log base e, because then I can rewrite it in its exponential form, where I can say e to the 5th is equal to x. And so I've solved for x. Another way that you could do that is you could use your cancellation equations, the idea of inverses. If I take that same problem, ln x is equal to 5, I'm trying to get rid of ln. What would undo ln? Its inverse, e, exactly. So I could go through and insert e on both sides. Now notice that I do have to insert it as a base so that these become my exponent, because if you look at your cancellation equation, it has to be e to the ln for it to cancel out. And so I have e to the ln over here. That will cancel out, and then I'm literally staring at my answer, x is equal to e to the 5th. So two different ways that I could do that. All right, so look at example number 5. Same idea. Solve the equation e to the 5 minus 3x is equal to 10. All right, so for this one, I need to get rid of e so that I can get to this x up here, right? So what's going to undo e? ln, right. So I'm going to insert an ln on each side. So I'll use those inverses, those cancellation equation ideas. So over here, ln e will cancel out and just leave me my exponent, 5 minus 3x. Like we saw right here, ln and e cancel out and just leave me the exponent. So 5 minus 3x is equal to ln 10. Now how do I get x by itself?
Subtract.
Yep, subtract 5 and then divide by negative 3. And a couple of different ways that you can write your answer, you know, that game of trying to match what they have in the multiple choice. So we could write it this way. We could pull that negative 1/3 out in front. You might see them distribute the negative through the problem so the signs change. So, all right, for example number 6, they don't ask me to solve. It says express ln a plus 1/2 ln b as a single logarithm. Express ln a plus 1/2 ln b as a single logarithm. So we're using those same properties of logarithms that we saw earlier in the lesson, and we're just applying the natural log to them. All right? So what do you do when you have a number out in front of a logarithm? What does it become?
Exponent.
The exponent, right? And then if I have two logs that are being added, I multiply them. Exactly. So you could write it as ab to the 1/2, or if you'd rather write b to the 1/2 as the square root of b, doesn't make any difference either way you want to go. All right, we mentioned that there are two logs that we use most often, and we have shortcuts for them. And that is a log base 10, which is the common log, so we don't typically even write the base 10, we just write log. And the log button you have on your calculator is a log base 10. We also mentioned log base e, which is ln, and you have an ln button on your calculator. But typically, like on a scientific calculator, you're not going to find anything other than a log button or an ln button. So what are you supposed to do if you want to find the log base 8 of something? There's not a log base 8 button on my calculator. And so that's where the change of base formula becomes helpful. The change of base formula enables me to take a log that has any base and rewrite it as a common log or as a natural log, because I would then have those buttons on my calculator to evaluate. So if I've got the log base a of x according to the change of base formula, I can rewrite that with whatever base I choose if I put the x in top and the a in the bottom, and I write it as two separate logarithms. So for instance, for this problem, the common log version of that would be log x over log a. The natural log version of that would be ln x over ln a. So if I've got something like the log base 8 of 5 and I'm trying to evaluate that, I can't do it like I was doing earlier in the lesson, because if I switch this from its logarithmic form to its exponential form, I can't get the bases the same. There's no way to rewrite 8 and 5 with a common base and set the exponents equal to each other. So that's where I would need my change of base formula. I could go through and I could say, okay, I'm going to put the 5 in the top and the 8 in the bottom and write it as two separate logs. And it would be your choice whether you wanted to use a base of 10 or whether you wanted to use the base of e, ln. It doesn't matter which one of these you get. If you throw this one in your calculator, you'll get 0.773976. Or if you throw this one in your calculator, you'll get the same thing. Now, when the new operating system came out on the TI, we got all kinds of new features, right? They weren't actually buttons on the calculator, but we ended up with some function buttons that gave us a whole lot of extra options. This is one of the happiest things that came along with that new operating system. When you use function F2, we got all of these little menu options. The very last one down there, number 5, is a log base. When you choose that, it literally puts on your screen log, and it puts an empty box right here and an empty box right here. In that way, you can type any base into your calculator that you want. And your calculator basically does change a base for you. So I can literally put the 8 in down here and the number in here and hit enter, and it will shoot out that correct value for me without me necessarily having to rewrite it as a change of base. So that's a happy thing. In essence, that just created a log base anything button on my calculator that I didn't have before. All right, we had learned earlier in the lesson 2 limit laws that dealt with logarithms. Those were for log base A. Now they go back and they rewrite those for me on page 432 as log base E. Literally, that is the only thing that changes about them, because the stipulation was if A is greater than 1, then these are your limit laws. Well, E is a number greater than 1, so I can put it in the place of A and nothing will change. So I can come over here and put E in for A and put E in for A, and I'll have the natural log of x. The limit as x approaches infinity of that is infinity. Or the limit as x approaches 0 from the right of that would be negative infinity, just like we had earlier today. So then that helps me if they ask me to evaluate a limit of a natural logarithm as well. So for example number 9, it says sketch the graph of the function y is equal to ln x minus 2 minus 1. And then that would be really helpful if they asked me to evaluate a limit after I had graphed that. So let's start with thinking about the graph. Here's our normal natural logarithmic function. Those 2 landmarks again, the asymptote and the intercept that we've been utilizing. So what is that minus 2 going to cause? Horizontal shift, right. So horizontal shift of what?
2.
Positive 2. What's the negative 1 going to cause?
Downward.
Vertical shift of negative 1, right. So horizontal shift positive 2, vertical shift negative 1. I'm going to use my 2 landmarks again. I'm going to take my intercept, and I'm going to go over 1, 2, and down 1 and draw that. I'm going to take my asymptote that was at 0 and go over 2. Doesn't really matter if you go down 1. It's a vertical line. It's not going to move. But I have those same 2 landmarks then as a guide for me to sketch that graph. So that would be what the graph looked like. So then for the second part of that question, they said, okay, now that you've graphed it, evaluate what the limit as x approaches 2 from the right-hand side of that function would be. And so I can come in and then say, okay, as I'm approaching 2 from the right-hand side, what is this going towards? Negative infinity, exactly. So that's how I can utilize those limit laws. And I also, we'll have some of them that I can do algebraic substitution on and utilize those laws as well. Okay, so here's our homework for tonight on pages 433 and 434. We're doing 1 through 37 odd, challenge 69. 1 through 37 odd, challenge 69.